Hello everyone, welcome to Sophus. Today, I'm thrilled to present a case study on House Pro, a leading home improvement retailer in the United States. We'll delve into their journey towards optimizing their network and inventory. House Pro operates an extensive distribution network across the U.S., employing a hub-and-spoke model. This network comprises one central distribution center, CDC, and 6 regional distribution centers, RDCs, essential for their diverse range of home improvement products. The company faces multifaceted challenges. Firstly, the demand patterns for their products are highly variable, complicating inventory management. Secondly, all distribution centers stock a full product range, resulting in elevated inventory levels. House Pro's primary objective is to restructure their supply chain and inventory allocation to minimize overall network costs. The objectives are straightforward. House Pro aims to find opportunities to reduce inventory and network costs without impacting service levels. They're considering a centralized stocking strategy for certain product groups based on ABC analysis, and are seeking to optimize inventory levels in line with this revamped supply chain network. For better understanding, we categorize products using ABC analysis, an inventory management technique that classifies items based on their significance to the business, like demand, cost, and risk factors. Class A items are vital, significantly contributing to sales volume or profitability, while Class B and C items are progressively less critical. Class A products account for 82% of total demand, with B and C class products comprising the remaining 18%. We'll now compare decentralized and centralized inventory deployment strategies. In the decentralized setup, the CDC distributes all classes of products to all RDCs. In the centralized model, the CDC only supplies Class A products to RDCs, while maintaining a full inventory of all products. Several key trade-offs must be considered. These include weighing transportation costs against inventory costs and balancing service levels with inventory optimization. Keeping B and C class products only at the CDC will increase transportation costs, as these can only be shipped from the CDC via LTL mode rather than nearby RDCs. However, this approach reduces inventory costs due to the pooling effect of centralizing the B and C class products. Another consideration is the trade-off between inventory reduction and service level challenge in the centralized network. Our methodology involved 3 steps. Step 1, network optimization. Step 2, inventory optimization, and Step 3, overall optimization. We developed scenarios for both decentralized and centralized models to compare their respective network and inventory costs. To construct a model for House Pro, we need clarity on input data, network optimization, NO, and inventory optimization, IO. Share some input tables, like sites, products, and customer orders. However, IO requires a fixed network as input, therefore needs more detailed policy tables, such as sourcing, transportation, and inventory, whereas NO can operate with more general all-to-all policies. The model includes 9 products, 152 sites and customers, and approximately 100,000 orders. However, policy tables differ between network optimization and inventory optimization scenarios. For instance, in the NO decentralized scenario, sourcing policies are minimal, indicating that all RDCs can source from the CDC, and all customers can source from any RDC. In contrast, the IO's sourcing policies are more detailed, with 1,301 rows specifying source destinations and products. This can be found in the NO's output in Step 1. This specificity is necessary because IO requires a predetermined network, unlike NO, which allows the model to choose. Hence, IO builds upon NO's output. We created scenarios for Step 1, Step 2, and Step 3 for both centralized and decentralized solutions. First, we run NO, using its output to establish suitable policies for I/O scenarios. Then we run I/O, analyzing inventory aspects like safety stock, which NO does not consider. Finally, we integrate IO's inventory output into the inventory policies table to create new NO+IO scenario policies. To aid understanding, we develop dashboards illustrating the costs, inventory types, and site breakdowns for each scenario. Returning to our slides for a summary, initially we observed that a decentralized network incurs lower transportation costs. The inventory types considered at this stage only include cycle stock and in-transit stock. We will need to run inventory optimization in the second step to evaluate the full impact on safety stock. This first step of network optimization creates a fixed network in the output, which will feed the inventory optimization in the second step. Inventory optimization offers a deeper analysis, considering safety stock against demand and supply uncertainties. Here, the centralized network demonstrated lower costs because of the efficiency of consolidation of Class B and C inventory into a single central warehouse. Ultimately, through combining network and inventory optimization, we calculated the holistic costs for each scenario. This analysis includes all types of inventory, revealing that the centralized network, despite incurring higher transportation expenses, results in the lowest total costs due to significantly reduced inventory costs. In conclusion, HousePro's journey in optimizing its network and inventory management highlights the importance of strategic planning via supply chain modeling, a domain in which Sophus particularly thrives. Thank you for your attention, and see you next time.